Okay, we're going to make our first tenuous connection between linear algebra and differential equations by thinking a little bit about derivatives and whether they're linear, and also something weird called the Wronskian, which tells us whether functions are related to each other. Okay, we talked a little bit about how when a matrix has a zero determinant, it's special. We can't invert it, and the equations that are built from it tend to be linearly dependent because it doesn't have it's not full rank, so its rank is less than its size if it's square, and that tends to give you a determinant equal to 0. Okay, doesn't tend to, it is equal to, equivalent. And let's now think a little bit about derivatives. So the derivative of, say, two functions, function 1 plus function 2, that's very much our form for checking whether something's linear. Is the derivative of the sum of two things equal to the sum of the derivatives? Yes, it is. This is one of the things that we do with derivatives all the time. We can distribute the derivative on term by term of the thing we're taking the derivative of. And then is the derivative of something times a scalar, a constant, equal to the constant times the derivative? Yes, it is. This is the way that we do all of our functions that are multiplied by scalars. So these two pieces tell us that the derivative itself is a linear operator. So we can consider taking derivatives as one of the operations that we might incorporate into linear algebra, and we can build something called the Wronskian. So the Wronskian is a matrix which is formed from a set of functions where you take increasingly high derivatives of that function. So let's suppose that the Wronskian is function number 1, function number 2, and so on, function number n. And I want to make a square matrix by taking the second row and taking the first derivative of the first function, first derivative of the second function, and so on, first derivative of the nth function, down to the bottom where I'm taking the nth derivative of the first function, the nth derivative of the second function, the nth derivative of the nth function. If you take the determinant of this, it tells you whether the functions are linearly dependent or independent of each other at that location in X. And it tells you a little about whether you can invert this Wronskian. And so that's part of the game of how you might solve things. And you can imagine that something like this is going to come up from our Taylor series, because if we had Taylor series of all these different functions, these are precisely the coefficients that are going into the Taylor series modulo the x minus a's, and which is the driving part, and also the factorials in the denominator. This is an awful lot like comparing the coefficient matrix of different Taylor series together. Hey, look, if we were comparing different Taylor series, those are approximations to the function up to the nth order. This Wronskian is like the coefficient matrix, or proportional to the coefficient matrix for the Taylor series of all these different n functions.